Very good morning. I'm Ashutosh from Indian Institute of Remote Sensing, and in today's lecture, we will discuss about map projection concepts and its application in the remote sensing and GIS. It is an important topic, and because we are doing various GIS analysis and generating various themes, so before that, we need to define our uh, proper coordinate systems and the projects or the projection system. So in today's lecture, we will discuss about that. So we take an example like in GIS, we are doing GIS analysis, and we need to construct suppose one school, and in the vacant land in the city, wherever it is there, and we have a certain constraints like the school should not be far away from the road, or we can say it should be within the 1 to 2 kilometer distance from the road, or we have another constraint: the school should be in the uh, medium density area so the students can approach there, or we have another constraint: there should not be any nearby garbage site. Hmm. And similarly, it should not be near to the like forest or agriculture. In that, like that, we can define various constraints here. So we can get the information of forest from the forest department, and we can get the information of road from the road department, or similarly the density information, wherever the population medium density is there, we can get the information from the municipalities. When we take these information from all these from the all the sources, then it comes in a layer, and when we put it into GIS software, it becomes like a GIS layer. When all the layers are not in the same projection system or the coordinate system, then the analysis whatever we are going to do may not be correct. Maybe you might have heard about the WGS84, you might have heard about the Everest or polyconic. So if they all are UTM, you might have heard. All these things are not, all the coordinate system of all the layers are not in the proper or same, then the analysis may not be correct. Okay, so we need, when we want to construct a school in the city, and we need the constraints from the different layers, there are the, and so all the layers should be in the same projection system or the coordinate system. Similarly, we can go for the, like we have a satellite images, and we are using these images. So before proceeding further, what is our requirement? As per our requirement, we can assign the coordinates or the datums system, projection system to the image. Then further we can proceed for the analysis. Another example, if I take, like you have a some, you want today you have generated or image, satellite image you have, but you want to compare with the some 100-year back images, but that is not digital, that is not the digital, that you have a in shape in the paper form. So what you will do, you will just take that paper form, paper image, and then you will bring it into the GIS environment. You will scan it, that image, and then you will put it into the GIS software. Then you will compare both the images. So when you will scan it, that image may not be having any coordinates, so you need to assign the coordinates to first that image, then and same coordinates you have to assign which you want to compare with the recent image. So both image then you can compare. And you are you might have seen on the Indian map that it is written like Everest and the polyconic. So Everest is the basically datum, and the polyconic is the projection system. You are generating your maps when by surveying, and after that, if you don't consider the curvature of earth, and then you bring it into the GIS environment and want to compare with the some existing map, the map may match or may not match, because if you see the coordinate systems are not same, the map will not match. So we will discuss all these things in the today's lecture one by one. So basic stats is about earth is around surface area is 510.1 million square kilometer. Mass of the earth is around 5.97 to 37 into 10 to the power 24 kg. and equatorial radius is 6378.137 kilometer, and the polar radius is 6356.752 kilometer. So with this we see generally our equatorial radius is, we I am telling that is the 6378, and polar radius is 6356. So what is happening, both radius are not equal. So that means generally our concept is like earth is looks like a sphere. If it had been a sphere, then the both the radius should have been equal. So if you see this radius and that radius, both should be equal, but both are not equal. So what we can say, it's not perfectly sphere. Earth is not perfectly sphere. So we will define what geometry it takes. There are the two three concepts as I explained to you. One is a, we need to define the earth first, which is a three-dimensional geometry, and when we convert this three-dimensional geometry to the paper map, that is a basically two-dimensional, the conversion or the transformation is called the map projection from 3D to 2D. We'll come to that. And flattening coefficient of around 0.0033528. Flattening coefficient, it is just a ratio of the basically about the major and the minor axis, and age is around 4.5 billion years. And elevation, if we see with respect to the mean sea level, it is 8848, it's Mount Everest. And there are seven tectonic plates, which are African, Antarctic, Australian, Eurasia, North American, South American, and the Pacific. This is a one picture we have taken from the space, and with this we can see the earth is basically it is not like regular surface. If you see the not like a smooth surface, you see somewhere mountains are there, somewhere valleys are there, and somewhere you see the mean sea level where the almost all levels are same. That way we can define it's not like a smooth surface, it is a basically a irregular surface. And the second thing, if we see from here, the it looks like an sphere because the difference was almost the 6356 and 6378, so around 22 kilometer it was there, which is not visible. It looks like an sphere, but it is not an exactly, it's perfectly sphere. For surveying and mapping, most of the measurements are taking on the Earth's surface. The surface of the Earth is an irregular surface. Directly using these measured values for the further computation of distances, area, volume will give wrong results because the irregular surface of the Earth is not mathematical. So when we are defining any measurement, doing measurement, we need to have some mathematical model. So our earth is representing as like an irregular surface, so first we need to define a mathematical model of the earth, then only we can do further computation on that particular mathematical model. So we need a mathematical surface which can closely represent our earth. So what we are doing, the irregular earth is there with us, and we are just trying to fit or push a one model into that earth which can closely represent our earth, which can be fit into that particular model of the earth. And then further computation we will carry it out on that mathematical model, which can be mathematical model is we can represent it by an equation. If we are able to represent it by an equation, then we can do further computation using that. So we need a model of the earth, and all the measurements can then be reduced to that surface for computations. Once the model of the earth is decided, we need to locate the position of the features. So when we are defining our earth model, and then we will define the positions of a features like one tree is there, or I am sitting here, then how much my height is there above from the what height my elevation is there, but my elevation is from where? It is from the maybe mean sea level, maybe from the geoid, or maybe from the ellipsoid. Anything can be there, so some reference point we need to define. Similarly, distance of a place from where? from where I am just measuring. My latitude, my longitude is there, suppose 78.3, or 78.1. So from where I am measuring, so I am defining certain position, like Greenwich meridian I have considered as 0, equator I have, latitude I have taken as 0, from where I am just measuring my coordinates. So we need some coordinate system, reference system, or that term for defining our positions. So now further we will go. We know that the earth is not perfect sphere or perfectly spherical. As I told you, the difference between the radius, like 6378.136 is the equatorial radius, and the polar radius is 6356. So around 22 km difference is there, both the in both the radius. So it is not perfectly sphere. So how to represent the shape of the earth? Now the question comes. The shape of the earth can be best represented by an ellipsoid. Now, shape of the earth can be best represented by an ellipsoid. So the question comes, what is an ellipsoid? My friend from the scientific background, they know very well, but maybe persons from the they don't know, they are not from the mathematics. I will explain the things. What is the basically ellipsoid? So you know that the circle is there, where the center of the circle is, suppose A, center A, and then the distance from center to the circumference, radius, it is called the radius, the distance from center to the circumference, and it will remain same throughout the circumference. So this is the basically about the circle, and double of the radius, the what we can what it will be, it will be a diameter. So it will be a diameter, and the equation of the circle we represent by x square plus y square equals to a square. So x square plus y square equals to a square. Now we go for the ellipse. In ellipse case, what is happening? You assume that the circle was there, and just we have flattened from top and bottom. Okay, just press it. So your shape of the geometry will be like, it will be a two-dimensional geometry will be a like this, and this is called an ellipse. Now in this ellipse, it is just twisted one. Okay, so what will happen? There will be a one center, and there will be a one vertex here. We can say this will be an vertex. This point we call it, and this is a co-vertex, and this is also co-vertex. And you see, wherever the diameter was double diameter here, with diameter was there double of the radius in the circle case, which has just shrunken. Now it has become smaller. So it will be a, it is called as a minor axis, and the distance of this minor axis is defined as the 2a, the small a and 2 multiplied by 2a, so 2a. And the horizontal axis, that is called the major axis, the horizontal the axis which we call it as a major axis. So it is defined as a 2a, or minor axis we are minor axis we are defining as a 2b, that is 2 into b, and the major axis is defined as a 2a. And now the equation of that ellipse is x square upon a square plus y square upon b square equals to 1. So if you see, if you see the b equals to a, that means minor axis, if it becomes, suppose, equals to a, the semi major axis, so the major axis. So what will be there? If b equal to a, then it will be a square, it is also a square, and this will go to the this side. So the equation will be now x square plus y square equals to a square. So it will be equals to circle. So if you see, if b equals to a, then this will become a circle. Okay, so if there will be any now if it is not different from that, b equals to a, then it will looks like a circle. So there is a just a little bit difference from the circle and the ellipse. Okay, now if you take the diameter of the circle and just rotate it about its diameter. Okay, they take the circle, rotate it about its diameter. what the three-dimensional geometry we will get? It is an sphere. Assume that if you are rotating a circle about its diameter, the three-dimensional geometry we will get is, it will be an sphere. Circle is a two-dimensional geometry where the x and y will come, and sphere will be an three-dimensional geometry where the x, y, z will come. Okay. And similarly, if you take an ellipse, what you do, you take the minor axis and then minor axis. Remember this thing, this is the minor axis, and rotate the ellipse about its minor axis. Then the geometry you will get is called an ellipsoid, or the specific name is the oblate ellipsoid. So our earth can be best represented by an oblate ellipsoid. For the geometry, you take about its minor axis, rotate about its minor axis, that ellipse, and you will get an oblate ellipsoid. Our earth can be represented by an oblate ellipsoid. And you can get about the another rotation also. You can rotate about its major axis as well, but that will be a polite ellipsoid. It will not be useful here. We are working with the oblate ellipsoid here. So I hope you understood the concept of the ellipsoid. It's a mathematical. Now ellipsoid equation we can define easily: x square upon a square plus y square upon b square plus z square upon c square. So what you want exactly? You wanted the mathematical model of the earth, and which you can be, mathematical model means like it can be represented by an equation. So we can represent it by an equation: x square upon a square plus y square upon b square plus z square upon c square equals to 1. This is an ellipsoid equation. So an ellipsoid is the mathematical surface which can be generated by rotating an ellipse about its minor axis. Such ellipsoid is called an oblate ellipsoid. Semi-major axis A, in ellipsoid we define the basically these many terminologies will be there. So semi-major axis is A, as I told you. This is the basically semi-major axis, the distance, horizontal distance from center to the vertex. It is a small a, and double of that it is called the major axis, which is defined by the 2a. And semi minor axis, similarly the vertical axis from center to the vertex, that is a distance, that is a b. Double of that is a minor axis, and it is a 2b. And eccentricity, eccentricity e square equals to a square minus b square divided by a square. Eccentricity is the another term by which we just show how the geometry is away from the circular positions. So is a square equals to a square minus b square upon a square. If you take b equals to a, b equals to a will be the if you calculate it, b equals to a square minus a square, it will be 0 divided by a square. So e will be 0. So E will be 0 when B equals to A. So B equals to A, it will be the case when it was there, when it was a circle case. So in circle case, the eccentricity will be 0. Sphere case, it will be 0. But when it comes to the ellipse side, then it will be lying between 0 to 1. When you estimate it, it will be 0 to 1. So it shows if it is a 1, if it is towards the 1, near to 1, that is highly elliptic. We can say highly elliptic, more pressed. And if it is a near to that, e equals to 0, near to that 0 point, then it will be a near to the circular. Okay, so that way we define the eccentricity. And the flattening shows how much flattening is there between that. So it is just a coefficient, f equal to a ratio a minus b, that is a major axis, semi major axis minus semi minor axis divided by the semi major axis f. So a reference ellipsoid has its center a close approximation of center of mass of the earth, and minor axis is parallel to the axis of rotation of the earth. So whatever the ellipsoid we are going to take, it is having a axis of rotation is the major of axis, minor that is minor axis. As I told you, the ellipse we are taking and rotating about its minor axis, and center is close to the center of the mass. Latitude, longitude, and the ellipsoidal heights are defined on this reference ellipsoid. So whatever the reference ellipsoid is there with us, in that we are defining our latitude, longitudes, and the ellipsoidal heights. That way we can see, this is the basically, you see the ellipsoid which we are fitting, the blue one, and the red one is the basically earth surface, the blue one. So we are fitting our ellipsoid into that earth. The best fit ellipsoid means it can best represent our earth model. Maybe somewhere elevation will be high, somewhere elevation will be low, but it is a mathematical surface. As I told you, we can represent it as a mathematics, so by the mathematics. So this that we need to define our further computation. And b is the semi major axis, it's like polar radius we can say. This is the this is the semi minor axis, b is the, so it is like a polar radius, and a is the basically semi major axis from center to the basically vertex, or this can be work as a equatorial radius. So now based on that we have a, now you know the concept of the ellipsoid. So based on that we can have a two type of ellipsoid. This ellipsoid is based on the measurement within a region, so it best fit that region only. The center of such reference ellipsoid does not coincide with the center of gravity of the earth. An example of such type of ellipsoid is the Everest ellipsoid, which was used in India. And the another kind of ellipsoid is there, that is the geocentric ellipsoid. As the name suggests, the center of geocentric ellipsoid coincides with the center of the earth. This type of ellipsoid can be used worldwide. An example of this type of ellipsoids are GIS 80 ellipsoid and WGS 84 ellipsoid. So there are two type of ellipsoids. One is a best fit ellipsoid, another one is a geocentric ellipsoid. So in best fit ellipsoid, what it was there, because local information was used to develop such type of ellipsoid. See, ellipsoid have a mathematical surface, and by any curve or any part, if we know, we can derive the equations like that. So we know the certain quantity and we can derive the equations, that way we can understand. And best fit ellipsoid means the local information was used to develop such kind of ellipsoid. And geocentric ellipsoid is the that today we have a various kind of measurements are we can take, and the geocentric ellipsoid by which we can develop geocentric, which can the center of that ellipsoid can closely represent our earth center. So earlier days when the Everest was developed, that time we measured only the Indian part. With that we derived the Everest ellipsoid. And similarly, the today's things we are having a various technology, like we have a GPS technology, we have a VLVI, and we have a lunar laser ranging techniques. Various techniques are there today by which we can derive our latest datum like WGS 84 and other. So geocentric, what will be there, since the local information is used in the best fit ellipsoid, it may be suitable for a particular region. It may not be suitable for the other region. The best fit ellipsoid I am telling, which was the basically like blue one. The blue one we see it may be best fit for the particular region, but it may not be suitable for the that region. But if you see the red one, the geocentric ellipsoid, it is a best fit for all the globe. Means earth is a basically earth surface, green is the earth surface, and if you see the red one, which is best fit all over the globe. And the center of the geocentric ellipsoid, that red one, which coincide with the center of the ellipsoid. But center of the best fit ellipsoid may not be, how much that depends on the ellipsoid to ellipsoid, best fit ellipsoid, how much it is away from the basically the earth center. So that kind of best fit ellipsoid and the geocentric ellipsoid we can define. But today things like we are using the globally we are using WGS 84, or these datums, the globally GRS 80, the globally accepted. So we are using the basically geocentric ellipsoid. And if we want our analysis in the locally, like local, we are using the Everest ellipsoid also. So local we can convert, we can transform one to another, it can be done. So about the Indian datum, as I was stating, the locally developed the best fit ellipsoid was there. The Indian geodetic datum used till few years back was realized during the 19th century. It was a result of great trigonometric survey carried out from 1802 to 1839. The conventional triangulation method was used and it was the best available technique at that time. The series of connected triangles from southernmost point of India up to the Himalayan foothills was used to compute the arc distance, what was named the Great Arc. The great arc measurements were used to determine the geometrical parameters, semi-major axis and the semi-minor axis, to define the reference ellipsoid, which was named after Sir George Everest as a Everest ellipsoid. This is locally fit ellipsoid with the following parameters. Now, as I told you, the best fit ellipsoid basically it takes the local information. So what India also developed in 18 that our basically locally ellipsoid from 18 we did the one great trigonometric survey 1802 to 1839. So 1802 to 1839, what we did, we have measured from Kanyakumari, means the lower southern point, to the top of the peak, like top peak Mount Everest. We have measured. We have done the survey, and like different arcs we have measured. I show you the picture actually. This was there, and you see it was from Kanyakumari to you see the top Everest we are going. That trigonometric survey we have done, and different arc were measured, and similarly from western point to the southern eastern point, and southern to the northern point. So that way we have done the trigonometrical survey, we have measured basically, and based on that we developed our ellipsoid. The local measurement was there, because that time if you see the globally measurement was not possible also. If you see 1800 years or 1802 1839, that time if you want from we want to measure from the other country, it was not that much so easy. So maybe other country also had developed the same type of ellipsoid or atom that as we developed from the top southern to the northern point we have measured, and then we created our ellipsoid. So they have taken the basically just to tell you that the two ropes and of around 20 miles, and then they have measured like this the angle, and then we have created one triangle. Then further these 2 points they have forwarded again and again. So like that they have measured basically, and based on that they have developed the great arc measurements they have done to determine the geometrical parameters. So what they have done, using that they determine the geometrical parameters. What is that? What are that? To define an ellipsoid, what are the things required? It is a semi major axis, minor axis importantly. So they have derived the semi major axis and the semi minor axis, and with that they defined one reference ellipsoid. It was the name as the Everest ellipsoid. So we were still using the Everest ellipsoid in maps, but now we are also switching over from the to about the from Everest to the WGS 84. So if you see the semi major axis, the Everest that time using the Everest the survey that developed the Everest ellipsoid, it was 6377301.243 meter, the semi major axis, and the semi minor axis it was there 6356100.231 kilometer, 231 meter. Now, in today's GRSAT ellipsoid, if we see the A is around 6378137 meter. So you compare that the both the semi major axis and the minor this today's GRSAT. So how much difference is there? 6377301, 6378113, around 800-meter difference is there. So at the time of 1801 or 1839 when the Everest was developed, and if we compare with the today's one, so it is almost only 800-meter difference is there in the major axis only. So how much we were close to the what we can say geocentric ellipsoid that time we have developed, and how much we were close to the this geocentric ellipsoid. So that way we can say that mathematics or the technology that time we were having in India, it was so developed, or we can say the it was close to the basically geocentric ellipsoid into the, if we compare with the today's work with the latest technology whatever it is available. Similarly minor difference in the minor axis as well. This was the trigonometric survey as we did at that time. Now we comes to the geoid. Geoid is an equipotential surface level surface of Earth's gravity field which best fit the mean sea level. So one was having a one ellipsoid. In ellipsoid, this is a mathematical surface. Ellipsoid by which we can transform, we can derive an equation, we can take the measurements from this over the surface of this. The another thing is that the geoid, which is not a mathematical surface, is depending on the basically earth gravity. Earth gravity is depending like mass is not properly distributed or some other factor it is there. So the it is the gravity is the like varying we can say, and it is very close to the mean sea level, very close to the mean sea level. When we are defining, we are considering so many factors like high tides, low tides, or the what we can say atmospheric parameters, all the things we are considering. But in geoid we are considering with only the gravity part, so where the gravitational potential energy remains almost same, the it's depending on the earth's gravity. So now for some of the measure we are taking this, and it is very close to the mean sea level. Now for the some of the measurements we are taking geoid as a reference point for the vertical measurement, or we can vertical means height. From the geoid also we can measuring the height, and similarly we are taking height from the ellipsoid as well. Okay, so various reference points are there. As I beginning I told you, as I'm sitting here, or any tree is there, or any chair is there, so what is the reference, how much altitude is there from that, what is the reference point? So reference point can be there either on the geoid or can be a ellipsoid, whatever it is there. Okay, and mean sea level and geoid both are almost same, because atmospheric effects we are not taking in this. It may be defined as the surface coinciding with the mean sea level in the ocean and the continuing under the land at the level to which the sea would reach if allowed to flow through frictionless channels. So it just means take the mean sea level and how it is going inside that earth and up down. So just create a one mean sea level, just approximate that. It will be a equivalent to the zeroid point. So now if you say like geoid and one is the ellipsoid. So one I have defined as a ellipsoid point, that is a mathematical surface. Another one is a geoid, which is based on the gravity. Now they both are tumbling each about on each other. Now if you say suppose geoid is h height, the geoidal height of any point is capital H, and if you take the geoid, the ellipsoidal height is the small h, and the difference between that is called the basically geoidal undulations. So if you see the earth surface, it is there, and inside that the one ellipsoid it is going, one geoid it is there, one height will be the from geoid, one height will be the from ellipsoid, and the difference is called the basically geoidal undulation. Generally, one point if we are representing horizontal, we are taking from the ellipsoid, it's like a latitude and longitude, and vertical we can take it from the ellipsoid as well, we can take it from the geoid as well, or mean sea level as well. So vertical we are having a various references. How we are defining a point onto the earth surface? So it is a suppose a point is P, we are drawing a perpendicular from point P to the onto the earth surface. So it will just like a line, ellipsoidal normal, this is a blue one which is hitting this axis here, and you see this is an equatorial plane. Wherever it will cut the surface of the globe or earth, you see one meridian will pass from here. So what it will be the observer's meridian? We already defined that is the Greenwich meridian is the 0 degree, and we defined from this Greenwich meridian to the observer's meridian, that is called the lambda, which is called the longitude basically. And similarly you take the upward angle from equator to the particular line, this is called the phi, and this is basically a latitude, this is a latitude. And similarly ellipsoidal height, it's the h, which is a perpendicular distance from surface of the ellipsoid to the point P. So this is a basically an ellipsoidal height. So somewhere it will be if geoid is passing from here, so it will take a capital H, it will be a geoidal height. So we can represent it as a height in the both the things. Now these things will be a latitude, longitude, and the ellipsoidal height. So the latitude, it is an angle subtended at equatorial plane by the ellipsoidal normal through the observer's point. Longitude, the angle between observer's meridian plane and the Greenwich meridian plane. Ellipsoidal height, the height above the surface of the ellipsoid, and measured along the ellipsoidal normal. So in this was basically what we are defining. Also the triode of axis we are taking, like x-axis is passing through the Greenwich meridian, x-axis, and origin is the center of the earth. Y-axis is a perpendicular to the x-axis, but it will be also in the equatorial plane. Both the axis x and y will be in the equatorial plane, and then z-axis will be the perpendicular to both the axis, or the axis of rotation of the earth, or perpendicular to the x and y. Okay, now we will define our parameter in x as y, and we can, these are called the basically the Cartesian coordinate, and we can convert from x y z to the curvilinear coordinate, that is the latitude, longitude, and the ellipsoidal height, and we can transform one to another. That's what I told you, we need some mathematical model. So we will use the, when once a mathematical model is there, we can use the equations to convert from this to that and that to this, like that. So now we have moved to the another part, which is the map projection. Now till now we were discussing about the three-dimensional concept of the earth, how to fit a model onto the uh, earth, and how we are deriving the latitude, longitude, or xyz onto this earth's surface. Now from this three-dimensional, when we are performing any analysis, we need to have a certain maps, and in maps every time we no need that like all India, the whole world should. So we will be main focusing on a particular area. We want that enhance that particular area, or maybe some other objective can be there. So we want in one specific map. So but in the three dimensional, it is difficult to analyze or measurement, taking measurement. What we are doing, the transforming of this three dimensional measurement of earth, or projection of the three dimensional earth onto a two dimensional sheet, is called the map projection. The transfer projection of three dimensional earth onto a two dimensional sheet is called the one map projection. So map will be a two dimensional, means there only will be a two things, x and y, maybe latitude or longitude. But in the three dimensional, there will be a three things, latitude, longitude, and the height, or x, y, z in terms of. But the transformation we are doing, projection we are doing, then we will have only x and y. So we will discuss about now the map projection. And in map projection, there are the various techniques to convert from earth surface to the two-dimensional map. We will discuss some of the with an example, some of the techniques with the examples. So transformation of three-dimensional space onto a two-dimensional map, a systematic arrangement of intersecting lines on a plane that represent and have a one-to-one correspondence to the meridian and the parallels on the datum surface. So transforming a three-dimensional space onto a two-dimensional map is called the map projections, and there will be a one-to-one mapping from the parallel, or what we can say, meridian longitudes, parallel will be the latitudes, the one-to-one mapping from three-dimensional to the two-dimensional. This we can do using the cone or cylinder, or directly also we can use the two-dimensional map. Some of the example we will discuss. So there are the types of projections. One is a equal area projections, maintain equal relative sizes, used for maps that show distribution or another phenomena where showing area accurately is important. The example is the azimuthal area or Albert equal area conic projection. There is another conformal, which is maintained angular relationship and accurate shapes over small areas, used where angular relationships are important, such as for navigation and meteorological charts, like Mercator, Lambert, Culver, Koenig, LCC. Equidistant, it is a maintains accurate distance from center of projection or along given lines. It is basically used for the radio or seismic mapping and for navigation. Examples are equidistant, conic, and equirectangular. Similarly, the azimuthal or zenithal maintains accurate directions and from a given central point and used for aeronautical charts and other maps. Where directional relation are important and mnemonic projection. So there are the various kind of various map projections are available. Now what is our objective? Based on that we select a particular type of map projection, like equal area. If we want a the whatever the area is there in that globe, we want to focus on to that only. The area should be remain same or in the some ratio onto the two-dimensional map, then we will use such type of map projection. If our purpose is to use the some shape should be preserved, shape should not be distorted more, so we will use the small area. For the small area we will use such kind of projection. Similarly, equidistant, the distance from a point to the another point when we are taking, then it should remain fixed. When we are going for the projection we will use the such type of projection. That's our objective basically. Similarly, in the directions we are taking azimuthal and it should be preserved. So based on that, various kind of map projections are available. We need to select as per our the basically requirement. Map projections can be classified based on their method of construction. There are many surfaces which are not plane but which can be created by a drawing a plane surface. So remember this map. There are many surfaces which are not plane, but what you can do, you can use such type of surface means geometries, and after that you unwrap it, then it will be end up with a two-dimensional map. Excuse me. Such type of surfaces are called the developing surfaces. So such type of surface we are calling as a developing surfaces, and the cylinder and the cone are the such surfaces. As I told you, the cylinder and cone can be used. They are the basically developing surfaces. They are not the plane surface, but we can use these surfaces for making a one two-dimensional map. So these are the developing surfaces. A map projection can be created by placing such surface on a globe, projecting the features from globe to the surface, and then unwrapping the surface to make a plane map. Now we are classifying this based on the nature, like plane, cone, cylinder. We can use the two-dimensional map, that paper or sheet for the projection, that is a plane. Cone, you can use the one cone, and inside that you push it one globe inside that, and then you project onto the wall of the cone. Then you unwrap that cone basically, or you take the cylinder, you place one globe inside that cylinder, then you project onto the wall of the cylinder, and then you unwrap it. So you will be end up with a one two-dimensional map. So this is nature wise. And the coincidence, it's a tangent, secant, and polysuperficial, where the tangent is the the radius whatever you are taking, cylinder radius, and the globe radius is see just like an almost equal. So what will happen, it will just touch the surface of the cylinder. You push that, you take the one cylinder, you take one globe, push it inside that, it is just touching to the surface of the cylinder. Okay, then this is a tangent case. Now you take the secant case. In that, cylinder radius is less, and then you the globe radius is more, and then you place into that the cylinder. So it will be that there will be a two lines which will be a basically there will not standard parallel. I'm going to tell this thing. So there will be a two standard parallels. And polysuperficial means we are going to use more than one geometry. And similarly, position wise, you place the normal, you place the cylinder like this is a normal case. You take the globe and take the cylinder like this, push it into that, and then you project, then you unwrap it. This is a basically transverse case. And the oblique means at any angle you can place that globe, and this is a basically an oblique case, different angles. So you see, this is the basically a example of the azimuthal projections. You take the map in the polar region, you put it like that, and then in on equatorial you push it like this, and in oblique case at any angle you can place it, so it will be projecting. So a particular part you can project onto that map, whatever your requirement is there. If you take the cylindrical case, the tangent, if you say take the, this is a basically cylinder, and inside that we have placed one globe, and you see this is the basically the radius here. Basically, it is just touching the surface of the cylinder, and this is basically a tangent case. And similarly, if you see uh, mm, the radius is of the cylinder is less, and it is cutting at two places. One is here, the dark one, dark blue, you are able to see, and one is here. So there will be a two standard parallel where there will not be any distortion. But when we are moving away, then we will have some distortion. Like this here also, like this, but here from there we will go up, so there will not be any here will not be any distortion, then distortion will increase slowly. So this is the basically second example. In the transverse tangent case, this is a transverse and tangent case, because you see it is just touching, so it is a basically tangent case, and if the cylinder is horizontal, it is a transverse case. Okay, and this is an oblique case, an angle you are putting, so this is an oblique case, and if it just touching the borders of that globe, so it is an basically oblique case, and the what we can say tangent case. Similarly here it can also have a transverse and the what we can say uh, uh, transverse case, and the secant case. Here also we can have a one two standard parallel or standard meridian, what you like that we can put. So just shrunken that, just place that small cylinder, so it will be a secant case. So secant case, transverse case, and the oblique case with the uh, transverse horizontal. uh, Conic projections, similarly we can have a one cone, and we can place it onto the globe. If it is just touching it, then we will have a one standard parallel, and when we are moving away, the distortion will increase the standard parallel. When it is a secant case, it is just, you see that there will be a two standard parallel to cutting that thing, and there will be a one, this is a central meridian, the which is touching about that, you are opening that flap, unwrapping that cone, and this is the basically tangent case and the secant case. These both cylinder and the tangent, the cone can be unwrapped after projection, so you will end up with the two-dimensional map. Many properties can be preserved on the Earth's surface. Some of these properties are area, shape, directions, and distance. Map projection can be constructed to preserve one or some of these properties, though not all of them simultaneously. Each projection preserves or compromises or approximates basic metric properties in different ways, and the degree and the kind of distortion vary with the projection used. Some projections are suited for mapping large areas that are mainly north south in extent, other for large areas that are mainly east west in extent. So there are the various map projections available, and the objective is that how to select that, what is our depends on the our objective. So if we want a particular type of study where we need to focus on the area, not shape, so we will use such type of map projection. The where we want to study about the shapes, then we will take the certain type of map projection. So uh, the map projection, when we will use, then it may preserve one property, and the other property may be in the partial mode or may not be also. So that way it can be there. So and a particular map projection can preserve all the properties, it may not be possible. So we need to select the map projection as per our basically requirement, and the degree and the kind of distortion vary with the projection used, which kind of map projection we are using. And so the distortion will depend on some of the map projection, the distortion for a particular area may be more, but the other may not be there. So if it is not that particular map projection, that particular part is not of our of use, so we can avoid that. We will take an example, then we will clarify this thing. uh, Property of the projection, like based on the intrinsic, equidistant, the distance will remain same, and the conformal, where the shape will remain present same, and the equivalent area, where the area will remain same. And generation wise, it is a geometric, semi geometric, and the mathematical. Geometrics totally depending on the geometry, and the semi-geometrics, where the equations can be used, and the mathematical, totally depending on the mathematical equations. So we will take examples of the cylindrical map projections. Like we will have a cylindrical map projection. So in cylindrical map projection, what I told you, we will take one globe, we will place into that globe, this globe into that inside the cylinder, then we will project onto the wall of the cylinder like this, and then we will unwrap that globe. So you will be end up with a two-dimensional map here. So cylindrical map projections are made by the projecting from the globe onto the surface of an enclosing cylinder and then unwrapping the cylinder to make a flat surface. And these the two important map projection under this cylindrical are the Mercator and the transverse Mercator. So in Mercator, what we are doing, we are taking a one cylindrical and map projection in a cylinder, and then conformal, where the shape will be preserved basically. So conformal, as I told you, the shape will be preserved. So meridians are equally straight line when we place project onto the wall, and when we unwrap it, so we will be having a map projections like this. So in that projection, what will be there, meridians are equally spaced straight lines. You see there are the longitudes which are having a equally spaced. Parallels are unequally spaced straight lines. Parallels, you see the equator. From equator, if you go up, these are the basically unequally spaced straight lines. And then scale is true along the equator. There will not be any distortion along the equator when we are going, and great distortion of area in the polar region. When we are moving away from basically what we can say equator to the pole region, then the distortion will increase. So if you see this area, can you recognize it? It is a basically a Greenland. And if you see an actual Greenland is, and you see the with respect to the India size, India is looks like a very small here, you see, and the Greenland is so much big, but in actual, what is that? No, Greenland size is very very small. So this is because of the distortion. So if our focus is only the near to the equator region, that may be the perfect one, but we don't want suppose polar region any analysis, so we can avoid this thing. But if we want to do any analysis, and which is big area is important here, it may not be suitable. We will go for the some another kind of map projection. So similarly, transverse Mercator, in that transverse case, we will take the cylinder as a transverse, and it's a conformal. Similarly, the shape will be preserved. Central meridian and equator are straight lines, and other meridian and parallel are complex curves. And for areas with lots larger north-south extent than east-west extent. So if we have a more east-west north-south extent, then we will use such type of map projection. We will not use for the east-west extent. Similarly, we have a conic projections, Lambert conformal conic projection, conical, conformal, and parallels are concentric arcs, meridian are straight lines, cutting parallels at right angles, scale is true along the two standard parallels, and it projects a great circle in a straight line. So if we see the conic projection, if we take the basically take the cone, and inside that place a cylinder or place a globe, and then we have a one standard parallel in the tangent case, two standard parallel in the second case. And if you project it, like look like this one, so meridians are here, straight lines, and these are the curves, basically latitudes are curves. So this is more useful when the area is having a east-west expanse. So basically it is a east-west expanse, like USA or some Russia or China, bigger maps if you which are having a east-west expanse, we can use this map projection. Similarly, we have a polyconic projection, in that we take the strips small cones of different size, and just one cone is touching just what we can say the globe, and we are taking one strips around that. And similarly the green one, we are taking a small strip. These are three, but we are taking close, and we are because if we are touching that particular place, then there will not be any distortion. Hmm. So if we are taking into distortion strips, so what will happen, there will not be any distortion. So like that stroke we can combine, and we can have some polyconic projection. And we have a azimuthal projection in the three partial equidistant conic maps, each based on a different standard parallel, therefore wrapped on a distant tangent cone. And when the number of cones increases to infinity, each strip infinitely narrow, the result is a continuous polyconic projection. So we will take the smallest strips into that, and then we will project complete map, and then it will be a polyconic projection. We have azimuthal projections. For an azimuthal or planar projection, locations are projected forwarded onto a flat plane. The normal aspect for these projection is the north or the south plane. Basically, this we are using for the, because flatness is there the north and south. We are using this type of plane there, projections there. UPS, Universal Polar Stereographic Projection, defined above 84 degrees north latitude and below 80 degrees south. It's a conformal, where the conformal means the shape will be preserved, and the meridians are straight lines, parallels are circles used in a conformal mapping of polar region. So this type of map will be there for the polar region, if you see. So meridians are straight lines, if you see, and the parallels are the concentric curves. So these will be a curves. We will have a concept of the grids, where distortion which should be remain in the particular grid. We want to minimize the distortion basically. So grid systems are normally divided into zones. That distortion and the variation of scale within any one zone are kept small. The examples are basically UTM grids, and before that we will have one concept of the false easting and the false northing. So if we have a central meridian and the parallel, and with respect to that, one origin is there, and if you see there will be a positive in this first quadrant, then second next will be a negative positive, third will be a negative negative, and then will be a positive negative. The quadrants we will distribute the points like this. So in this quadrant the points will be the negative negative. So once these are the negatives, and we want to make it with respect, we want to shift the origin somewhere. This is the with respect to that particular coordinate system origin. So it with respect to this origin, if I see these points may be positive. Okay, so with respect, but this is not the exact origin, so we are shifting origin from this to make this point as a positive. So this difference is called the false easting and the false northing. In concept we are using, and same concept we are using in the UTM grid. If you see, these are the basically grids, small the here 8-degree difference is there latitude wise, and the 6-degree difference is there longitude wise, and we have created in a particular grid, particular case of basically transverse Mercator projections. And which grids we are coming, and we are defining in the numbers within that grid. So we are not respect to the 00 latitude or longitude, within the grid only we are defining. So because of that we are shifting our origins, and choosing a map projection, as I told you, depending on our requirement, like east west expanse, more USA map is there, if you see, then the LCC map projection will be more useful, and the cylindrical map projections will be more useful with for the UK. So it depends on the location, shape, size of the region, and the theme and the purpose of the maps selecting a map projection. When we are defining a map projection, we need to define projection parameter as well. To define the coordinate system completely, it is not sufficiently simply to name the kind of projection used. It is also necessary to specify the projection parameters as well. And it is important to know the projection and the projection parameter used in the map imageries. Sometimes it is required to superimpose one map or image on another map. If map imagery are different projection parameter, the details will not match if they are superimposed. The set of parameters required depends on the kind of projection. Projection parameters, in that we will define which is the what is the central meridian, what is the standard parallel, what is the false easting, false northing, how much you have shifted the horizon, and the units, whether it is in minutes or degrees, and the reference ellipsoid as we discussed in the beginning. So reference ellipsoid, whether it's a best fit ellipsoid like Everest kind of ellipsoid, or it is a geocentric ellipsoid, it is a kind of WGS 84. So all these things we need to define when we are giving any parameters to the person. And we have a earlier we having open series maps and defense series maps. Earlier in open series maps we were using the polyconic and Everest. Now we are in UTM WGS 84, and DSM we are having a polyconic Everest to the LCC. We have switched over a polyconic Everest to the LCC and WGS 84. So we need to project the spatial data for any analytics, make it possible to use data from the different sources, and several projections are there from where we have to choose, and the projection inevitably distorts at least one property. So we need to select such a projection which we want for the particular type of analysis, because whatever we want to preserve, can choose suitable map projection which can control the scale error or minimize the distortion. So with this, we will conclude here. Thank you very much.